then we'll start up once it's going.
Okay, sweet. I think we're all good.
We're good.
We are good.
Okay, sweet. So we are New Rocketry. So we're from Newcastle University, Australia. Just to quickly, briefly go over the people in the room. Over here running the Zoom at the moment, we have our team leader, Kobe Noble. Behind me, we then have Josh Morman, who is our recovery lead. So he covers both the physical recovery and also the electronic recovery. We have Mark Batterham, that is our structures lead. And then we also have Lennox Taylor, that is our payload lead. And then as our staff members that we have here today, we have Malcolm Sidney, who is in the bright orange jumper, who is our senior technical officer from the university. And then we also have Dr. Dylan Cuss-Kelly, who is our academic advisor from the university. And then
Great.
myself, I am Austin, and I am the chief engineer this year of the team. Okay.
Lucky you.
Yeah. So we've been reviewing some of the other past video reviews, and we've noticed there's a couple key things that you hit on in pretty much every single one. So we've done up a brief slideshow just to hit those key points for you. So, and then we'll do the whole nose to tail of the rocket, if that works for you.
That sounds like a plan.
Perfect. I'll get Kobe to go through it. Okay, so just a brief overview of the rocket. So we are running a 4-inch diameter rocket this year. I'll go over it briefly in the next slide, but we have had a change in the booster design from technical report 2 until now. Pretty much it has, it's just a straight 4-inch rocket now, and then it also has an internal section that includes our avionics bay and our payload. If you want to go to the next one, Kobe, thank you. So the change in booster design. So originally we were going for a transition design from 4 inches to 3 inches, as you would have seen in technical report 2. But we unexpectedly lost access to our academic that was an expert in CFD that was going to help us develop our CFD analysis to determine the separate flow separation over the transition section. So we decided, because we lost access to that it wasn't a safe decision to try and fly that during our test flight, as we didn't have any validation of the flow separation. So we changed our design to just accommodate for a straight 4-inch design, so that our simulations from Open Rocket would be valid and acceptable.
Okay.
So to start off with, in our nose cone section, as you can see, we have one of our recovery points up there in the nose cone section. It is made out of 6061 aluminium. We got it machined here at the university, and it is both bonded and epoxied up into the nose cone. So it screws up into the nose cone's joint. We have an example version here that we'll go over with you when we do the nose to tail of the rocket. And it holds our topmost recovery point for the rocket. Also, we have our coupling part epoxied in using West Systems epoxy, and the coupling length is 1 caliber.
How did you prep the inside of the nose cone? Because you have a little for bonding and stuff. Because you have some accessibility issues.
Yes, so prepping the inside of the nose cone, thankfully we were able to get down there because the nose cone isn't extremely long. So it was sanded with different grit sandpapers, I think ranging from, was it 200 to 240 grit sandpaper. And then it was cleaned up with isopropyl alcohol before we then bonded it in.
Very good.
So on the design of it, you can see it has ribs out of it, and that's to create a mechanical lock as well once the epoxy itself has cured, so then the actual aluminium part can't just be pulled straight out of the epoxy.
Excellent. And that is a forged die bolt that I'm looking at?
Yes, correct.
Excellent.
All right. Perfect. All right, so this is just an overview of our separation points to make it easier for you to understand once we get to separating it later on. So our main parachute is stored within our nose cone, and it separates from the top of our body tube forward. And then our drogue parachute is stored within our booster section that separates from the bottom of the body tube. Sorry.
Okay.
So just to go over our internal structure, it's what I have on the table here in front of me. It consists of the top half being our avionics stack. So that includes our safety critical things like our Ravens and our GPSs. And then our payload is then stored in the bottom half of our internal assembly. And they're both joined together, but still kept as separate entities and inserted into the rocket as one unit. And then as you can see, we have our charge wells and eye bolts on either side, at the top and the bottom of the entire payload.
Okay, and we'll see the hardware later on.
Yeah.
Okay.
So just an overview of our avionics. So it consists of 2 Blue Raven featherweights, 1 Apogee Super Simple GPS, and also 1 featherweight GPS. And to touch on the batteries, we're using 18650 lithium-ion cells that are mechanically locked into their holders. So you might see on the drawing there that there is a plate that sits above them that fastens down on top of them so they can't move.
All right. When you say 4 of them, is that 1 per electronic module or?
Yes.
Okay.
1 per electronic module. So they all have their own battery.
Okay. So there's 4 batteries total, but one 18650 per module.
Correct. Yes.
Okay. Very good. And we're just going back briefly on the picture there. I'm not sure if I can see your cursor or not. I think I can see your, no, that's my cursor. You can show me where the battery, I can see your cursor. Where are the batteries going?
So the batteries are the purple ones on the CAD model and the light blue colored cylinders on the actual picture. Down to the very bottom of the stack.
Okay, I see them down there.
And they're held inside of 18650 holders.
Okay. Is there any tie wraps or anything that keep them from moving out of the holders?
Yes, so I don't know if you can see our cursor, but it's hovering above it at the moment. So just above the batteries, there is an FR4 plate that goes across the top of them, and that's fastened down to hold them into the battery holders.
Okay, so there's no play, no potential for movement for the batteries to move out of the holders.
No, we can also demonstrate that if you'd like once we go through the actual physical prototype.
Okay, we'll look at it when we look at the hardware. But okay.
Perfect.
All right, keep on going. Looking good.
These are our electrical schematics, but I'll get Josh to touch on those when we go through the actual avionics stack itself with him.
Okay.
So get through these ones, Kobe. They're just there so we can bring them up properly for you. Our payload, I will get Lenny to go over for you when we go through the rocket, but it is a technology demonstration payload, which is pretty much consists of a linear actuator and a pressure chamber, and it replicates the pressure outside of the chamber inside of the chamber. So on the outside of the rocket to the inside of the chamber.
Okay, what kind of pressures are you looking at internally?
Lenny, pressures
30,000 pascals max.
Okay, I'm gonna have to interpret that back into PSI.
We can quickly do that for you now if you'd like. While I keep going along. But Lenny will do a full overview for you. He's calculated all the safety factors and that of the pressure vessel and everything.
Okay, so
it also only runs after it reaches apogee. So it's only on descent that it's running, so it doesn't affect flight.
okay, so there's no energetics in the payload. There are is there RF in the payload?
No, there is not.
Okay, so from a safety standpoint, there's nothing in the payload that should be considered hazardous.
Yes, correct.
The conversion is 4.35 psi.
How many PSI?
4.3.
It's low, so that's fine. Okay, very good.
Okay. So for our fin attachment, we use a similar methodology to prep the fiberglass tubing and our fins. So it's sanded with 240 grit sandpaper, then cleaned off with isopropyl alcohol before bonded with West Systems epoxy. For our fillets, we also use West Systems epoxy filler inside of them to hold their shape properly. And then on top of that, we also laid up 3 layers of 200 GSM carbon fiber on top of that for a tip to tip.
Okay. Don't see any issues with the fin installation at all. One minor concern on the West Systems, since your minimum diameter Do you know, have you heard of the term class transition temperature for epoxies?
Yes, so we aren't actually minimum diameter, we're only running a 75 mil motor, so we do actually have FR4 centering rings between it, so there is a gap between our motor, our
Okay.
front motor tube and the external motor tube.
Okay, that would be my only worry about using West Systems. And I see it looks like you've got an Aeropack retainer on the back end of the rocket.
Yes, correct, I have a slide on that one as well.
Okay, because I was going to ask what epoxy is holding that in.
Yes, so we have a flanged one, if you just want to step forward, Kobe. So we have a flanged motor retainer, so it's held in there with nylock nuts that also have West Systems epoxy holding them on as well, so epoxying them in. So even if
I'm
the
good with it.
fail, it would still have the nylock nuts there holding it in.
Okay, because my worry was if you were using a type of Aeropack that mounted over the tube, if you were using West Systems for that, I had a little bit of concern about temperature there.
Yeah.
Okay, while we're looking at it here, tell me about your launch lugs. How are they held on?
Our launch lugs are held in the same fashion as the motor retainer itself. So it has a nylock nut on the inside of it, and there's also epoxied in there as well.
Okay, and that's forward and aft.
Yeah, so that's for our aft, and then our forward one is bolted into our rearmost bulkhead inside of our rocket. So it goes
very good.
Airframing into the bulkhead.
Okay, I'm good.
So this is just a video of our drogue black powder test. So this is a test at 3.2 grams, I believe. At 3 grams, and we finalised with 3.5 grams for our actual flight test that we'll get to. Just so when you see that it hasn't quite popped out as much as it should.
Okay.
And then that is our main parachute black powder test as well.
Okay, looks like you got plenty there.
Yes, correct, correct. And then we successfully test launched this rocket as well. And this is just a graphic of it going off of our launch rail. As you can see, it's very windy. And then I believe on the next slide as well, we also have a video that will show a bit more of the flight. Here it goes. So as you can see, at about L+2 seconds into the flight, there was an oscillation that occurred. So it was an extremely windy day, which also didn't help with wind cocking. But at the same time, we were also using not our ideal motor. So the intended motor for this is an L2200, and we had to use an M1101 motor because of the motor availability. Thankfully, our mentor, Brad, was able to supply us with a motor that we could test on. But because of the motor availability in Australia at the moment, we had to test on that motor. So it wasn't ideal, but as simulated, we were expecting that oscillation to occur, but we knew that it restored itself from the simulation.
Okay, just out of curiosity from your test launch, did you run the numbers with the M motor and how well did you correlate with your simulations?
Yes, so we did run the numbers. So M motor was to get to
9,800 feet.
to 9,800 feet, and we went to 9,985 feet.
Sounds pretty good.
Yeah. Also, we aligned with our main parachute, like velocity under main parachute and velocity under drogue as well. So they were both within the bounds required in the DT.
Okay.
All right. So that's the rocket after we successfully recovered it. So we recovered it, thankfully, not too long after. And that's part of our team there with the rocket. The only part of recovery, though, if you want to go to the next slide, thank you, Kobe. We did have some minor zippering occur inside of the rocket. So as you can see, it's only about 10 millimeters. I'm not exactly sure what that is in the imperial conversion.
Just under half inch.
Just a little bit less than half an inch.
Yeah. So we have already made, I have it here, we have a new body tube already made to replace the one in the rocket. So we can fly at Spaceport with a new body tube, and we also have a new U-bolt design that brings up the axis of rotation of the shock cord. At the moment, the U-bolts, as you'll see when we do our showing you the whole rocket, sit down inside of the body tube a little bit. And we've now brought the U-bolt up slightly, so then when it rotates around, if it's caught by the wind, it's not pulling down onto the tube anymore.
Did you inspect your shock cord for any damage, or did you replace it?
So there, we do have installed in this one that we can also show you the shock cord used on the day, but we also have ones to replace it with. So there was minor fraying along the shock cord, but we have several replacement ones to use for Spaceport.
Okay. Are you going to put any kind of a buffer around the? Well, we'll see the other stuff there. Do you need to put any kind of a buffer around the shock cord so if it rubs against the tube, it has some protection?
Yes, so we also do have nylon tubing that we could use if we needed to do that to put around it, so that if it were to rub around the edges, that it wouldn't fray itself.
Okay. And that's is this your only defect from the launch?
That was the only defect. So we had nominal flight other than that, and we also had nominal deployment events.
One bad raven.
I heard one bad raven. How so? How was it bad?
One raven didn't give us full data. It only recorded for about 12 seconds. We're not sure why. We saw in one of the other video conferences that's happened so far, somebody recommended bonding the cap down to the board completely. We think it also probably could have been something around that because we lost power, but we were reading fine both before flight and after flight, so we're not quite sure what happened.
Okay, did it operate the pyrotechnics it was supposed to?
The first Raven did, yeah.
Okay, but the second one did not.
No.
Okay. Are you?
Sorry, quick question. Was the batteries are soldered, aren't they?
Yes.
Yeah, the batteries are soldered.
Yeah, cool. Okay.
Are you using the same Raven for your SAC flight, or are you going to replace it?
We're going to do some more testing at some of the NPR launches we've got coming up. So we'll be testing both the Blue Ravens. If we don't get good data, we'll do one Blue Raven and one Raven 4 because we've used the Raven 4s in the past and we have pretty good confidence in them so far. So we'll do some more testing in a month or so, or just under a month at our local kind of low power launches. And we'll see if we can fix the issue. If we can't fix the issue, we'll run 1 and 1. If we can't fix the issue, we'll just run both Blue Ravens.
Okay.
Perfect. So that's all we had to go through for the slides. So I'll get Kobe to start operating the portable camera now, and then I will get Mark to start off with starting to go through the airframe structure from the nose cone.
Okay, so what we'll do is when we go through the rocket, let's kind of go through it like the sequence would go in flight as far as any deployments or anything.
Perfect. So we'll start from the nose cone. Mark will go from there, and then Josh will do all the recovery stuff for you in order.
In terms of events,
Yeah. All right.
So what we got here, these are S-rad tubes that we've made. You saw previously the new tube that we're going to be replacing for the body tube. These were made from fiberglass using West Systems epoxy, and as we said earlier, it's got the tip-to-tip carbon fiber. So during flight, the launch rails are aligned here at the aft section and up here on the aft bulkhead.
So just a couple questions real quick there. When you reran your simulations, so what is your speed off the rail now?
It's 38.3 meters a second.
Okay, so that's about 100 feet per second, if I got my math right.
It's 125, yeah.
Okay. All right, that's good. And what's the rocket weigh for launch?
It weighs 17.1 kilos.
How much again?
17.1 kilos.
38.
Okay, so times 2.2, so 34.
Yeah,
So about 38, 39 pounds.
that's correct.
Okay. All right, and this is a bare tube next to the rocket?
Yes, so that's one of our bare tubes before painting. That's the one that will be replacing our body tube.
Yeah.
That had the zip ring in it.
Okay. All right, keep going. Sorry to interrupt you.
That's right. So our first separation event will be for drogue, and it will separate along here. So we've purchased some couplers from Wildman, and they have been bolted into the booster section, and then shear pins for the body tube, so it will separate this way.
What are you using for shear pins, and how many?
4, number 4, and 40 threads per inch in the drogue in the rear, and then 8 in the front.
Okay, so you're using I'll call it SAE or United States 440s.
Yeah,
Yes.
yeah.
Okay, you're not using metric threads for that. Okay, so you're using 4 at this joint. Do you have any venting for the compartment for atmospheric pressure?
Yes, we do.
Yes, static pressure ports.
Okay, and all right, so you separate here.
Yep.
Can you drag out your parachute stuff? Like to see some of the recovery stuff there. And like this, does it? Okay, so very good. All right, it just falls out, which it should.
Yep.
Looks good. Looks good. And are you using any? Okay, you've got that there. Okay, how big are your black powder charges? I think you said you had. You upgraded the.
3.5 grams for the drogue deployment and 3.6 grams for its backup. And then for main deployment, we have 4 grams and 4.1 grams for its backup.
Okay. All right, keep on going.
Sweet. So yeah, this descends under drogue until we get to 400 meters, at which point the nose cone will separate. With that.
And you said you had 8 shear pins up there?
Correct,
Yeah.
8 of the same 440 shear pins.
Yeah, and that was mainly decided because with our previous test launches, we've had main separate at apogee, so we
Okay.
want to mitigate that factor by putting more in, and hence why it's a 4 gram charge for the main.
Okay, and when you did your ground tests, you had the shear pins installed, correct? Okay. And you said you verified your descent rates earlier. What is your descent rate on the drogue?
95 feet per second under drogue and 25 under main.
Okay, coming down a little bit faster than I would like personally, but you're well within requirements.
It's close to the requirement, and because it's such a light airframe, we're on one of the smallest drogues we can get.
Okay. Oh yeah, 95 feet per second on the drogue, I'm fine with. 25 feet per second on the main is a little bit faster than I would personally use, but you're well within the requirements.
Yeah.
So no issues.
Yeah.
Just an observation.
Okay.
Okay, you've got swivels for both of your parachutes?
Yes, correct.
Yes, that's correct.
Okay, so how is the on the booster end, how is the shock cord anchored onto the booster?
To the motor tubes forward. Now.
Okay, so going onto the forward bulkhead of the motor?
Correct, yes.
Probably best I'll take it.
You will be
Okay. Okay. Are you going to use any tape or anything for your shock cords for flight to try to ease packing?
Sorry, could you
What
go
was that?
again?
Sorry, they were doing the motor.
Okay, that's good. All right, I'm good with that.
What was the question? There was a little bit of rattling going on, so we couldn't quite hear very well.
Are you going to use? You just had all your cords come out at once. Are you going to use any kind of just some, masking tape or anything just to kind of organize the shock cords when they play out, or are you just going to pack them carefully?
It's not the plan. Yeah, we don't have any experience doing that. We packed them pretty similar to how we had it over in here. That's worked for us on both previous flights and this one too.
If you're successful, I'm not going to change you. It was a question.
Yeah.
That's all it is.
we haven't done it before. Maybe afterwards we can have a little chat about how that works, how you implement it. But we haven't done that specifically before, so.
Okay, you've got a working plan here. I'm not going to change what you know works.
Cool. Perfect.
I'm happy to help out there if you want, guys, at next launch. I can show you.
Perfect. You know that record, see that? That one. Yeah.
Okay, so that's the airframe. Like to look at the payload.
Yes.
Payload and the eBays.
Structure? Perfect. We'll start off with the payload because Lenny's up with it at the moment. He'll give you a brief run through of it.
Yeah, so with the payload, we have our linear actuator here, the student design chamber here, a PCB with all electronics up in the top section.
Okay, and what kind of batteries are you using for these electronics?
It's 4 18650s put in series.
Okay.
So battery pack.
Okay, so one question I had looking at it, I see on the eBay, you've got all thread going through all the layers there, holding it together. And then you've got your payload. What is holding the eBay and the payload together so that when the various forces are applied, they don't separate?
Here we've got an M10 bolt and nut there.
Okay, that's going up into the electronics there.
Yeah. So on either side of it. So they can come completely apart so that we can adhere to the payload being completely separate to our recovery.
Okay. Okay, so what I'm looking for is the load path between the front part of that section and the back part of that section.
Yeah. So we have bulkheads on both the front and bottom, and then.
Okay, one comment, and this is strictly a comment, don't change anything, it's just something to keep in mind for the future, is you've got electronic connections in where you've got your black powder charges.
Correct.
And I'm speaking just personally here, it's not a complaint or something you have to fix. It's a practice I personally don't like because black powder residues are corrosive. And over time, you could get into intermittent connections there.
Yeah, so all of the external components are going to be replaced for the next one. So these were just what we had bolted onto it for this previous launch, and you are right, the barrier blocks are corroded. They were pretty seized when I was putting them back together today. So we have the cable pass-through is the only way gas gets through down into here, down in this section here. And we have it sealed up with blue tack. And it did a pretty good job in terms of when we inspected it, the black powder hadn't made it much further than these plates. And we didn't have any clumps or anything like that further on down in any of the electronic components.
Yeah, I usually use something that we would call plumber's putty in the US. To seal gaps like that.
Yeah.
Okay. It looks solid. Let me look at the electronics just a little bit again and look at the batteries and stuff there. I'm looking primarily on the avionics.
Yeah. Cool.
Okay. So could you just roll it about 90 degrees? I just want to see for the circuit boards from the side. Okay. So are the circuit boards sitting on standoffs?
Yep. Nylon standoffs.
Okay, excellent. Because what I'm looking for is because some people, and I don't like the practice, have bolted circuit boards directly to their sled, and they're putting load and stuff on their solder joints and everything, which I don't like.
So these circuit boards are just power distribution throughout the system. So they take inputs from the Ravens, the batteries, and then spit out our outputs for the apogee and main barrier blocks. We've got two of them, one for both Ravens, and then down in this section in here. So these ones on this plate, there's just two of these exact circuit boards. We're trying to get it a little bit. Two of the exact same circuit boards, and then on the backside is just the power transfer for the GPS. So they have external connectors which come up to the screw switches up here. Each screw switch controls one battery, controls one circuit.
Okay,
And these have static pressure ports in the airframe that we can turn these on from the outside.
okay. As far as and you've got enough venting that your Ravens get that area gets enough venting for proper sensing of the atmosphere.
Yep.
Yes,
So the pass-through hole, plus also there's a through hole for the wires that come. It might actually be really hard to see. You got to get in here. We've got a through hole from the top of the. Yeah, it's going to be too hard.
Yeah.
We've got 2 through holes on the top of this plate that take our inbound and outbound from the PDBs to the screw switches.
Okay, looks good. So one other question on the nuts that are holding the those large nuts that look like they're holding the U-bolt up forward.
These ones?
Yeah, do they have any locking devices? Are they nylon or do they have Loctite or anything?
Loctite, yeah, on both sides.
Okay, okay, on both ends. Okay, looks good. Okay.
The batteries have solder tabs on them, which I spot welded onto the batteries, and then we solder the wire connections onto them as well.
Okay.
In terms of movement, they can move laterally. So these particular holders come with stock with wires. We've taken out the contacts on the sides, and we just rely on our power transfer directly through wires on those solder tabs. So they can move not up and down, side to side in the holder, but that doesn't have any effect. And even still, they're relatively tight, but they can move, I suppose, this way.
If you've got the wires actually soldered to the batteries on solder tabs, that's excellent. I'm good.
Yeah,
with that.
the holders are mainly there just to have something to keep it
physically hold the battery.
Yeah, nicely placed on the airframe. Austin talked a little bit about this particular tab here. So we've just taken the diameter, the whole diameter of the circle of the airframe, and then just cut down the side. And they sit flush on top of the batteries to keep them not very compressed, but keep them on top of the holders as well.
Okay. Well, the fact that you've got when I first saw the picture, I was worried about that type of battery holder with the batteries, but since you've got the wires soldered to the batteries, I'm not worried.
Yeah. We also don't particularly like the contacts because they're a bit springy.
Yeah, I don't like the spring contacts. I would say to a first look, it looks great. So just looking, I'm not sure if you can zoom in on one of the terminal blocks where you've got wires attached on one of the boards.
On the top or in the PCB?
On the electronics, actually one of the PCBs. One of the printers. Yeah.
So the Raven ones will have a 2x3, and then 2 1x3s and a 1x2. The 2x3 handles the Raven inputs, so VCC, ground, and then all of the commons or the fire channels. And then the batteries next to that, then you have a 2 4 and 2 aft.
Roll the top 90 degrees towards the camera. That's what I want you to do.
It's a terminal block.
Okay, because when I'm looking at it, and I'm assuming that this is color coded for wiring, that it's not just whatever.
Sorry. Yep.
Okay, that's good practice.
We have a document internal that has the colors and where they go to and all of that.
Okay, one thing, have you been doing pull test on your wiring to make sure that they're secured?
Yeah, terminal blocks are just rough. Typically, we use the cable ties to help give a little bit of relief here.
Okay, because one thing, if I were to be inspecting the rocket physically when we go out there, and I'm looking at this particular one, and I'm looking at the blue wire, I may see just I can't tell for sure on the blue wire there. There may be a little bit. There's a little bit of exposed conductor on that wire, so it's not catastrophic, but we probably would ding you during an inspection to ask you to redress that wire so we don't see any conductor at all.
So we have a whole new wiring harness. We've got both a spare one and a new one for Spaceport. These are the ones that we used for the test launch, but we've already gone ahead and made a new set just so we can throw them out, especially for as you were saying with the corrosion up the top, we can get rid of
Okay.
that. We can replace the whole thing.
Okay, but again, just one thing that we do look at when
Yep.
we're doing the inspections is we'll look for any exposed conductors and stuff at terminal blocks.
Yep. Is there any good way to sort of fix that terminal connection?
Just make your, strip is, just, make sure what you strip and what you put the wire in, that there's no conductor exposed. There's
Okay.
no magic formula.
Yeah.
Okay. It looks excellent.
So yeah, both Blue Ravens, and then 2 different GPS.
Okay, very good.
And
And the
then,
GPSs, so the featherweight is on a license-free channel. What about your other system? I'm not familiar with what frequency you use.
both of them are 900 megahertz.
Okay,
This is, so you've got a featherweight GPS, but you've also got an Apogee GPS.
okay,
It's the super simple GPS. It comes with a really big handheld device.
okay. You've done a nice job packaging this stuff, your wiring harnesses and everything else. So kudos to your team.
Thank you. We think so too. Thank you. Do you want to look at the top?
Yeah, let's look at everything here. Okay.
Because we're interfacing with barrier blocks here, from the internal wires, we've got ring terminals, and then the E-match ends have just spade connectors on them, so they're easier to put on when you're
Okay.
and then
Okay.
one barrier block controls one Raven, the other barrier block controls the other Raven. It's slightly different on the other end, because we changed from 4. That is the yeah. Oh wait, hold on. That's the side I was talking about. So this one's got 3 barrier blocks instead. So the 4 barrier block controls the commons for both Ravens. So they're jumped in between, and then the pyro channels are run through the 1x2 barrier blocks.
So just a brief concern, they're actually sharing returns on the Ravens?
They're jumped with, right this way.
Do you have a schematic? They have a schematic that shows it. That would be the best
Yeah,
way.
there's actually no connection between any of the circuits except for the E-matches, but the E-matches only do 1 Raven per E-match.
Okay, if we can go back to the schematic, if you had the schematics or something, I'd like to go look at those again, just to better understand it.
Yeah.
I'll pull it up.
So the idea was to just keep everything completely isolated from itself. So we have.
Yeah, they should be totally isolated.
Yeah. But in terms of the GPSs as well, we had the same philosophy with just keeping it all completely separate.
Okay, so this is Raven 1.
They're both wired the same way. The only difference for the 3, the bulkhead that has 3 barrier blocks is that instead of the 2 and the 3 coming from the same barrier block as the VCC or the common, they're on their own separate one, and the VCC is on the 4-channel barrier block, but the barrier blocks, the barrier blocks don't share internal circuitry. There's little metal clips that go over the top of them that we use to jump.
Okay, what I was confused on, I thought the Raven 1 and Raven 2 were sharing these stuff, and it's not. That's what I was confused by. Okay, you're good. You're good. I forgot that you can hook up multiple channels on the Ravens.
Yeah.
Yeah, I forgot that Ravens can do that.
And all of that output stuff is handled on our power distribution boards. So they've got outputs for the forward and the rear barrier blocks.
Okay, so anything else to look at on the rocket?
I don't believe so. You two don't have anything you want to cover?
Besides the main being 60 inches and the drogue being 18, that's probably, and then 40-foot shot cord for both.
Okay, and your distances are such that the pieces can't hit each other during the deployments.
Yeah, so we've actually got them set up kind of like a J. So the kind of off-center loop is used for the nose cone. That's what connects our nose cone. And then the parachute's connected all the way up in space. And then the other connections on the eBay. And then we have a similar idea here where the offset loop. Can you stop? The offset loop is connected to the eBay, and then the parachute's off in space, and then the like 2/3 length is used to connect the eBay to the motor retainer.
Okay. All right. So after looking at the rocket, the last area is, and let's just talk about it. I don't need to look at it here. Is checklists. So what checklists do you have?
Kobe has those ready to share now. So we have 6 different checklists, Kobe,
Yes, we
that
have.
are completed to be submitted in with the technical report when I think it's due tonight. So we'll be submitting it this afternoon.
Get out of this.
And Kobe will just bring them up now to give you a brief little overview of them.
So they're all roughly this sort of structure, but we have like our assembly one, just to track traceability and make sure everything's correct when we get there. Kind of made so you don't have to think as much when you're doing these. It's like, yep, that step is done. Anyone can sort of do it. So we have an assembly checklist, pre-flight checklist, launch mishap.
Okay, let's go. The launch checklist is what interests me. What are you going to do with the launch pad?
Oh, so I guess our launch checklist is more, okay, once it's already integrated onto the pad. Our pre-flight one is more that, so we can have a look at that if you would like.
Okay.
So yeah, before we go to the pad, verify everything's safe. It shouldn't have been armed anyway, but it's just another double check, and that our assembly's been completed. We've kind of got all of our documentation done, got permission to go to the launch area, double checking all of our shear pins are still in, making sure they haven't fallen out while during transportation.
Are the shear pins threaded in, or are they just pressed in?
So we have super glue. There's a dab of super glue under the shear pin heads to hold them in, but this is just a check. We don't expect them to fall out, but we think it's worth double checking.
Okay.
That.
Okay.
Yep. So it's, yep.
One suggestion, I mean, you're fine with what you have. You can always do an appendix or something. There is, what is the beat pattern that you're expecting if all is well?
Yep.
So that's just something you could do it as an appendix. You're fine with what you have. It's just an add-on.
Yep. Yeah.
The Blue Ravens also have pretty good integration with your phone, so you can verify they're on your mobile device as well.
Okay. By the way, was it in the earlier checklist? You don't need to bring it back up to verify that your batteries are charged or replace batteries before you fly?
Yes. Yeah. We check the voltages on all the batteries on the payload and avionics right at the start of the assembly checklist.
Okay. All right, so you switch everything on, igniters. Okay, we'll install your flyer of record will install igniters. Okay, I like that you're mentioning about touching the leads together. You know, as I call them, flashing the leads. That's a good step. Okay, that looks good. So now you're on the pad, you're ready to fly. At the end of this checklist, it looks like. So
Yep.
my question to you is, do you have a procedure or a checklist if for some reason we have to remove the rocket from the launch pad, like the weather goes bad or something? Do you have a checklist to safe the rocket before you remove it from the launch pad?
Yeah, so we have a scrub / just the flight has failed to launch. So in that checklist, which I can also pull open, is kind of two things. Either we need to we scrub and we take it off the rod and kind of back to the launch site. But then there's also one for igniting installation, the process we do that just in case we get an igniter spit or not ignite the motor correctly.
Okay. All right. Can you scroll down a little bit there? Okay, looking at it. Okay, so you're hooking, that's a bad igniter. So if you're scrubbed, you're switching off the primary Raven, you're switching off And the secondary Raven rocket is safe. Hello. Okay. Very good. Very good. I like this. Okay, I like your warnings for the PPE. You're looking great. Okay, so for now, when you fly the rocket and you recover the rocket, do you have procedures to verify that there's no live charges left in the rocket when you pick it up?
Yeah. Yeah, so we have our whole recovery checklist as well, which goes through the process of also like picking up the packs, what we need, documentation, that sort of thing as well in that. But to go down specifically for that, we have this section.
Very good. Very good. Okay. Yeah, you've got it covered for checklist. Very among the better jobs I've seen done. Very good.
Thank you.
Okay. Anything else that you have for me?
Don't believe so. Is there anything else you need to see?
Nope, I don't think so. I think we've gone through the rocket. I think we've seen everything. You guys have done a very professional job. You've got a good looking rocket that's been well thought out here. You've got your testing done basically. You're gonna still do some additional flying, it sounds like. So all I can say is we'll see you in the US in June and wish you guys the best of luck.
Thank you very much.
Thank you for your help.
Thank you.
Okay, I don't have anything else for you. So it's
Yeah.
still midday for you, but
Yeah, have a
Me.
nice night. Yes, thank you for taking the time to meet with the team. Thank you for the feedback, and thank you very much for doing it at what, 10:30 at night your time?
no, it's not even 8 o'clock here at night.
No, it's only 8. Thank you very much for the time and the input of the team. We greatly appreciate it.
Okay, well, have a good day now. It's not evening for you, so have a good day, and you guys did a nice job.
But thank you very much.
Thank
See you,
you.
Spaceport.
Well done, guys.
Okay.
That was good.
Enjoy the
Okay.